Hello, everyone. Thank you for joining us for today's USEA Consensus Program webinar, Sustainable Water Management for Decarbonizing Fossil Power Generation. My name is Alex Krauke, and I'm a consultant for the U.S. Energy Association's Consensus Program. The Consensus Program, established in 2008, seeks to educate the public, policymakers, industry, and other stakeholders, and build a consensus on the wide array of benefits of carbon capture use and storage, as well as cleaner coal technologies. This program is done in cooperation with the U.S. Department of Energy's Office of Fossil Energy, and we carry out the work through a series of briefings and webinars, such as today's, workshops held monthly or quarterly, various reports throughout the year, as well as a monthly news clips that we send out. If you are not already on our mailing list and would like to subscribe, please feel free to email my colleague Michelle Littlefield at mlittlefield@usea.org. During the webinar today, we will be taking questions. However, due to time constraints, we will wait to answer them until the end of the webinar. If you do have questions or comments, please enter them into the Q&A box at the bottom of your screen. And please include who your question is directed towards. That usually makes it easier for us to determine whose turn it is. So with that, I'm going to pass it off to NETL's Briggs White to go ahead and introduce our speakers as well as today's program.
Very good. Thanks, Alex, and thanks to USEA for hosting us for this important webinar that's really going to focus on what are the implications with respect to water management of decarbonizing fossil power generation. We're going to look out into the future and try to understand, as we try to mitigate carbon emissions, what does that really mean? What kind of technologies, what kind of challenges, what kind of opportunities lay ahead? And we've got two great speakers with us. I'll introduce them in a minute. In terms of objectives, we're going to talk a little bit about what the department is doing in the water space. We will also, as I said, share some information and some perspective. Going to highlight a funding opportunity towards the end. And really importantly, we want to hear and learn from you. So as Alex said, I really encourage you to please provide your input, your feedback and commentary in the Q&A function throughout the talk so that we can really learn from you. So like I said, we have two really great speakers. After myself, I'm the technology manager for NETL for the water program, as well as our materials and energy storage programs. You're going to hear from Megan Motter. She's an associate professor of civil and engineering at Stanford University, and she's also the research director for the National Alliance for Water Innovation, which is funded by, again, DOE and the Advanced Manufacturing Office. And we're also going to hear from Tim Scone. He's a senior environmental engineer, again, with the National Energy Technology Laboratory, and he heads up our life cycle competency at NETL. So to provide a bit of motivation, here domestically, a number of states as well as utilities have made commitments with respect to clean energy, reducing carbon, et cetera. We see states with clean energy mandates, renewable portfolio standards, decarbonization objectives. Some of them are focused on carbon, some of them are focused on renewables, but you get the picture. There's a significant groundswell of enthusiasm towards decarbonization. And around the world, folks are thinking about, well, how do we do this? And two of the leading candidates are switching the fuel, in other words, a decarbonized input to the process. And one example could be hydrogen, another one could be biofuels. As well as on the back end of the process, how do we capture the carbon and mitigate it through technology such as carbon capture and sequestration. So here you see just some notable achievements around the globe. For example, Air Products with their large build out in Saudi Arabia, using renewables for green hydrogen, where they're going to create ammonia and send that around the globe. In the United States, we're doing significant work on CCS, over 20 million metric tons per year sequestered in terms of carbon sequestration. In Europe, notable national billion-dollar level commitments to hydrogen, building out pipelines, hydrogen storage, et cetera. So a significant groundswell of support to investigate these technologies that are going to be needed. And we don't know which ones are ultimately going to be deployed everywhere. And around the world, there's going to be a mix of resources that are going to come into play as well as demand sectors. And to bring it back to water, we don't know exactly what the water implications are. And so that's why we need to look into it, because after all, water is not uniformly available around the globe. And so this webinar is to say, as we look into the future and we focus on decarbonization of fossil power, what does this mean for water management? What are the demands? What are the needs? What are the challenges? What are the opportunities? So with that, I'm going to turn it over to my colleague, Tim Scone, who's going to lead us through some information in an NETL perspective. So Tim, it's all yours.
Thank you, Briggs. I appreciate it. And I look forward to the conversation today, and particularly the Q&A that's coming. My goal today is to help impart to you some thinking about where the intersection of greenhouse gas mitigation as well as the water intensity associated specifically around thermoelectric power generation. So first of all, the words and the things that I expressed today are my opinions and not necessarily those of the Department of Energy. And what I want to start with is really kind of taking a step back. You know, as a child, I was always taught that the earth is 2/3 water, and that's kind of a cliche that we've heard, and something that you see when you look at the globes and other things is all of this available water. Our fellow colleagues at the U.S. Geologic Survey put together this perspective to help us understand really what is that magnitude of water that's available really to support life on our planet. And so of all of the water that's available, only about 0.8% of the Earth's water resources are suitable for supporting human life and other life forms. Of that 0.8%, only 0.9% of that is considered liquid fresh water from lakes and rivers. And so if you look at the picture on the left here, and you see the large blue globe, that's the amount of water that's actually available in relationship to the total volume of the Earth. The very small blue dot sitting over Atlanta, Georgia, where my arrow is, that is the total amount of fresh water that's available on the planet to support human life today. And so as we think about the cliche of the Earth is 2/3 water, the reality is that is not true. Our water resources are extremely limited to support life, and we need to figure out how to conserve and protect those resources effectively. With that context, this is not a new problem. Our fellow colleague, both at the global level and at the national level. At the global level, the United Nations Environmental Program has identified that water is fundamental to life on our planet, but the precious resource is increasingly in demand and under threat. Water, from the UNEP perspective, has been identified as the 6th Sustainable Development Goal. And when we look into the targets underneath that Sustainable Development Goal for our planet, we see that targets like increasing water use and efficiency and ensuring fresh water supplies, implementing integrated water resource management, and protecting and restoring our water-related ecosystems are core drivers related to the thermoelectric industry today. And once again, reaffirming the need for the work to minimize our water footprint. Similar to our colleagues in the United Nations, at the national level, the U.S. Environmental Protection Agency has come out and talked to us about how climate change is changing our understanding about water resources. And as the climate warms, the atmosphere altering the hydrologic cycle, changing the amount, timing, and intensity of precipitation will continue. What this tells us is, while we think of the needs today around water, it's only going to become a more scarce resource going into the future. This underpins the importance of today's discussions. Today, we're going to set a little bit of a stage for our conversation around the role of water in electricity production, for those that aren't as familiar. We want to touch on an understanding of the life cycle water intensity of electricity production. We'll talk about decarbonizing thermoelectric power generation, and then the water intensity of the thermoelectric power sector in a decarbonized future. And then we'll opine on some concluding remarks and opportunities. At a national level, we would typically talk about water in terms of the water withdrawn and the water consumed. withdrawal is the amount that is extracted from a water body to support our purposes. In this case, cooling of a thermoelectric power plant. Water withdrawal, once again, our colleagues at the USGS conducted a study in 2015 that identified that water withdrawal for thermoelectric takes about 41% of the total water and consumes right now about 34% of US freshwater resources. That's about 133 billion gallons per day. And most of that is coming from freshwater with just a small amount for saline. So an opportunity to significantly reduce our amount of water withdrawal today. But water consumption is a different puzzle. Water consumption is only about 4% for the thermoelectric fleet, where irrigation dominates that from that perspective. The magnitude of water consumption is also much smaller than that for water withdrawal, in the sense that it's about 4 billion gallons per day per USGS in 2015, and current estimates around 2018 put it around 2.6 billion gallons due to some retirements in the thermoelectric fleet between those time periods. Still, 2.6 billion gallons is a lot of water that we need to effectively manage, particularly given population growth and other competing demands. I also want to, in the understanding around water and power plants, we're going to be introducing a couple of concepts. And so I want to talk about the differences and about how water is used and how we handle cooling water in most thermoelectric power plants. So water is really heated in a boiler to produce steam that turns a turbine and generator to produce electricity. After the electricity generation, the steam is condensed using a separate cooling water stream. That cooling water stream is either directly discharged back to the source body of water. This is often referred to as once-through cooling, or could be recycled in recirculating cooling towers to lower the water temperature to improve heat transfer. Another option is dry cooling, and there are some stark differences. And so the table on the left is to help kind of paint the magnitude of the differences between the current cooling water management strategies. Once through has very high withdrawal comparatively, but very low or near zero water consumption. And it's relatively cost effective in the sense that after the condenser, we directly discharge back to the body of water. Recirculating cooling towers, on the other hand, do require mechanical draft towers to be built and managed and operated, but their water withdrawal is much smaller, around 600 gallons per megawatt hour, but the water consumption is about 500 gallons per megawatt hour. Significantly different than our once-through cooling systems. Now, dry cooling has been developed and deployed in arid regions where water is really scarce. Now, there is a clear trade-off here between water availability and cost of management of that versus the cost to install and operate dry cooling systems. Now, I'm proud to say that over the research that's been done over the past decade or so, we are seeing dry cooling costs come down, but there's still a lot of opportunity for improvement in that space. To get some perspective on what types of assets are out there in the thermoelectric fleet today from a cooling water perspective, the following graph shows kind of the history of that installation from that perspective between 1950 and 2016 in this perspective. The blue line is once through, the orange line here is with the recirculating cooling towers, and a red line is the dry cooling. There are some hybrid systems out there. What you can see is that once-through cooling is starting to be reduced, and we've seen a lot more of the recirculating cooling towers in practice in the fleet today. I want to switch gears for a moment and talk a little bit about the life cycle water intensity of electricity production. So to set a stage, this is the US electricity production for year 2018 power generation. And on the left, what I'm showing is the water consumption of each of these types of technologies in liters per megawatt hour. Now keep in mind, these are in liters per megawatt hour, so they are equivalent for the delivery or production, excuse me, of a unit of electricity. I am also showing what the percent of the generation contribution was next to the labels, so you can get an understanding of what the magnitude is if you multiplied that through. So hydro jumps out the bottom of the scale as being a very large number, but something to keep in mind is that has to do with the evaporative losses from the lakes and reservoirs that are used to support the hydroelectric fleet. Today, I'm really going to be focusing my conversation on the traditional thermoelectric steam generating units, which is the coal, nuclear, natural gas kind of aspect. And we also see that solar thermal also has a significant water consumption aspect associated with it today. Given the focus of the talk around decarbonization, we're also going to be juxtaposing the water consumption data along with the global life cycle global warming potential of the different technologies. At the fleet level, we provide an assessment here, and this is based off the reported data for the current fleet on a life cycle perspective. As we move forward in the conversation today, and we start to talk about some of the decarbonization options that exist for thermoelectric power generation, I am going to be talking about these on a per megawatt hour produced basis, and we'll be providing results in the context of each individual technology's profile and not at a fleet level, something to keep in mind. So today, and Briggs set this up well, as we talk about carbon capture, utilization, and storage, or that post-combustion capture of carbon dioxide from the combustion of the fuels as one of those strategies for carbon reduction. We'll talk a little bit about biomass co-firing with a supercritical pulverized coal-fired power plant or coal plant. And we'll talk about advanced conversion technologies and their potential role. And I've picked two here, fuel cells and hydrogen to power. One thing I want to note at this moment is that these are not intended to be an exhaustive list of all of the reduction opportunities that exist, but to set the stage for the conversation that we're going to have in the Q&A around this dichotomy of decarbonization and what it means for water intensity to provide the power that's necessary to drive our economy. So let's get started. Let's talk a little bit about carbon capture, utilization, and storage. And so when we add CCS to an existing power plant or put it onto a power plant, that additional water is needed for the increased parasitic load on the power plant to operate the carbon capture and compression systems. And so I want to focus your attention on the graph on the right-hand side. And this will be a consistent theme for this graph for a couple slides, but the black dots on this slide are going to reflect the current baseline technologies of reference that I'm going to be referring to. In this case, it's a supercritical PC, coal-fired power plant, and I've remarked a natural gas combined cycle power plant, both without CCS. And then the orange circles reflect the technologies with the advanced or the decarbonization strategies employed. In this case, a supercritical PC plant with carbon capture and storage. In this case, we're modeling geologic storage in a formation as opposed to utilization. And also the same thing with an NGCC with CCS. And so we can see some trends here. As we add carbon capture, we get a significant reduction in our greenhouse gas emissions on a per megawatt hour basis produced, but we see an increase in our water requirements as a result of this increased parasitic load. Now, to help support this, we've provided a table here as well. It talks about the percent change in the life cycle greenhouse gas emissions and water consumption of these different technology options. So in the case of the supercritical pulverized coal plant with CCS, the comparison case is the same plant without CCS, and that's equivalent for the natural gas combined cycle plant. So we can see here significant value from the carbon capture, but opportunities that are going to add increasing demands on our limited water resources that we're going to have to effectively manage to make these viable solutions. Moving forward, I'd like to talk a little bit about biomass co-firing. So in here I'm looking at it with a bituminous coal plant. And so I'm taking that same supercritical pulverized coal plant, which you can see remarked in the lower right-hand corner with the black dot. And here we're looking at adding biomass to that, 20% by weight, 35%, and 49% by weight. And so the dots, the orange dots directly above that reflect the increase in the water consumption and the reduction that you see in the global warming potential by adding different levels of biomass to the plant and co-firing it. Where we really see our significant benefits, though, is the combination of co-firing both biomass and coal with CCS. We now can see significant reductions in our global warming potential, even though we see strong increases in the water consumption in order to enable this. That additional water is really needed for the biomass growth, as well as for the operation of the CCS system, as we discussed previously in that slide. Let's move forward and talk a little bit about advanced conversion technology options that exist for decarbonization and how that reflects to water management. So here we're going to be talking about a solid oxide fuel cell, and it's important to remark that that produces electricity by a chemical reaction instead of combustion. However, recirculating cooling towers are still used for heat transfer and are the primary source of water consumption. When we talk about hydrogen production, both hydrogen production and combustion consume water. Hydrogen production by electrolysis also requires water as a material input, in addition to cooling of the combustion gases. So here I've changed the frame, the reference point. So I just want to point that to your attention, that I've chosen here for the advanced technologies in this case to compare them to the NGCC with CCS, as well as to note that the scale, the x-axis scale here is also on this been changed from 1,000 to 350 kilograms of CO2 equivalents per megawatt hour. And so here we can see some trade-offs between different hydrogen production methods and solid oxide fuel cells. One scenario that's often touted and discussed is that with excess renewable energy being available during off-peak times, that excess renewable energy can be used to produce hydrogen. In this case, the hydrogen is acting as an energy storage device, which then can be stored and used when needed and combusted to produce electricity without CO2 emissions. And so here I've also added the data point of hydrogen production using a polymer electrolyte membrane and electrolysis powered by wind. And so you can get that perspective as well. So moving forward, I've just now taken all of the different data points that we just discussed from the different technology options and kind of laid them out on one slide. And when we think about that water intensity going forward, the future really is unclear around which technologies will really be the winners and which ones in which areas will help drive into those markets. The other important thing is that I've only described to you today the juxtaposing greenhouse gas reductions along with water conservation as opposing objectives for thermoelectric power. Ultimately, what gets deployed into the market will take into account a much broader sense of priorities around cost, the need to build out infrastructure, resiliency, reliability, and other metrics of societal concern. And so by no means am I attempting to say that these are the only things of importance to help drive and think about it in our future for technology selection. But as we think about it in terms of water conservation, our choices for decarbonization strategies and how we obtain those will have an effect on our water availability and water conservation. And we need to think about that in the totality of all the scenarios that we're looking at. I've chosen today not to project or predict what the future will look like for deployment, but rather wanted to paint the picture for you today about how these two are in contrast and what opportunities there are to explore in this space. And next, I'd like to kind of think a little bit about some concluding remarks and opportunities and kind of really drive home a couple points. And that is that the future really is uncertain, but growing demand for energy is certain. That decarbonizing the economy is a priority, decarbonizing thermoelectric power is a priority, decarbonizing thermoelectric power will increase water intensity in almost all scenarios. And that low carbon strategies today call for a reduction in fossil-based thermoelectric power without carbon management, where I would challenge that an effective carbon management strategy will enable all types of energy to be effectively competed in the market so that we can still achieve the same goals of decarbonization. We know that the economic and life cycle environmental performance will drive technology change to help meet these future priorities. And most importantly, for today's perspective, the sustainable water practices remain a priority today and into our future. So last of some concluding remarks and opportunities is that I see real challenges in front of us. The challenge is meeting this growing energy demand of population and the planet in our country. There's significant challenges in reducing greenhouse gas emissions and the timescales that we're discussing and are necessary. There's also the challenge of sustainably managing our water resources to support life, that water intensity and our role in thermoelectric power. So what opportunities do we have for water reduction? And I've limited these specifically to water reduction. And that's existing power plant water reduction strategies, dry cooling cost reduction and performance improvements, evaluating alternative water use. We talked in the very beginning about limited fresh water, the ability to figure out how to cost effectively with a low greenhouse gas footprint, be able to provide additional non-freshwater resources for use. It would be significant. Looking at hybrid thermoelectric and renewable power plant concepts, as well as innovation. And I can't stress that enough. There's so many opportunities today as a community yet to explore as we put our work together to help improve and decarbonize and manage our effective water resources, whether that's demand destruction, regional water scarcity alignment, hydrogen opportunities, or other advanced power plant concepts. The good news is that there's a significant amount of work going on in this space, and there is an increasing need for research and work in this space if we're going to continue to sustain life and provide the energy resources, even in a decarbonized world going forward. With that, I'd just like to say thank you very much for your time. I look forward to your questions and the conversation in the Q&A, and I will turn the presentation back over now to my colleagues. Briggs, I've relinquished control for you.
Great. Well, Tim, thank you so much for that very helpful introduction. I am Megan Motter. I serve both as an associate professor in civil and environmental engineering at Stanford, as well as the research director for the National Alliance for Water Innovation. And so in today's talk, I want to highlight some of the very important work that NAWI has done over the past year, really identifying ways in which, as Tim alluded to, innovations in how we use water at plants and innovations in the technology around water treatment might support the power industry in some of those decarbonization objectives. So I'm going to begin by just giving you a little bit of background about NAWI, some overview of the road mapping and baselining processes that we used to inform our research priorities over the next year. And then I'm going to transition into where I have extended some of NAWI's analysis in my own research group to cover other aspects of the water-power relationship. So NAWI has the mission of securing the nation's water supply through energy efficient and cost-effective water desalination. What we're seeing across a whole range of industries is that changing precipitation patterns and increased water demand, aging infrastructure and regulatory requirements for discharge are really forcing water users to turn toward non-traditional water sources. One of those sources is actually on-site reused water. And so NAWI's mission is to secure the nation's water supply and achieve technologies that enable 90% of these non-traditional water sources to realize pipe parity. Achieving that mission is sort of centered on how we define pipe parity. So I would like to just emphasize that we see pipe parity as kind of acknowledging the reality that when and where and how a water user acquires water and decides which source to tap is very much a function of both the marginal cost and energy intensity of the full life cycle water supply, as well as other sources that are available. What's the portfolio that they have to choose from? And it's often very specific to the end user and the geographic region that that end user is operating in. So we decided to pursue these road mapping efforts by sector. One of those sectors was the power sector, although certainly some of the insight that we gleaned from the resource extraction sector is important from a fuels perspective. But here, I guess I would emphasize that while cost and energy really remained at the core of NAWI's quantification efforts in these baselining activities, we also heard over and over again about the role of some of the softer value propositions like drought resilience or sustainability certifications or reliability that are often actually driving the use of some of these non-traditional sources, and in many cases incentivizing users to pay a premium for those non-traditional sources. So we conducted a really thorough data collection and analysis of that data for the power sector with the mission of really understanding the drivers of non-traditional water use and some of the key challenges that would face the power industry if they were to implement and adopt more of these non-traditional water sources. I want to highlight the fact that there are 3 different contributions. There were a set of core NAWI team members that were a part of this, survey contributions by a very, very large number of contributors. And then we conducted follow-up interviews with technical experts in each of these water sectors. So for the power sector, we had 28 experts in a workshop that was held over 2 days, and 11 individuals that were willing to really share with us through in-depth interviews their insight into where these challenges and opportunities lay. I want to just call out Amy Childress at USC and EPRI, who were really the leads on these power baseline and road mapping efforts. We can't thank them enough for their support and their wonderful leadership of this. I am just a messenger on this side. I also want to emphasize that NAWI will release the full set of baselining data and road mapping results in later Q1 of 2021. So please be on the lookout for that. You can find this on our website at nawihub.org. The sort of key conclusions and really high level takeaways from this, because I don't have time to go into what's nearly 100-page roadmap at this point, is that there are really 2 drivers of these non-traditional water sources in the power sector. The first is inadequate or low reliability freshwater cooling supply. And Tim and Briggs both alluded to this. What we're seeing around the US is that, well, the vast majority of water sources for power for the power sector remain sort of traditional fresh surface water sources. We're seeing an increasing reliance on reclaimed water, saline water, and brackish waters for cooling water capacity. So we expect that to continue to grow, especially in places where reliability there's a premium on the reliability of these wet cooling sources. The other big driver for non-traditional water reuse in the power sector is regulatory compliance. And here we're really looking at avoiding discharge and moving towards zero liquid discharge particularly at coal-fired power plants, in order to comply with a whole host of regulations related to the effluent limitation guidelines, cooling water blowdown guidelines, the Clean Water Act 316B. So, there's a lot of pressure that plants are feeling to mitigate some of these discharges. And when that implementation or adoption of ZLD is sort of helping with that compliance, it's also generating this very pure water source that can be used in other parts of the plant. And so there's a bit of an upgrading aspect to some of that wastewater. We also use this opportunity to understand what are the real treatment challenges, both from a technology perspective and an adoption and implementation perspective. And what we saw is that, one of the big issues is that we're seeing big seasonal shifts in cooling water sources and cold sources that will necessitate very adaptable treatment trains. So these cooling water intake or other makeup water intake treatment trains are going to have to deal with variable concentrations of foulants and scalants that are coming from these different sources, particularly silica chlorides, nitrates. And then we're also seeing a really variable concentration of regulated trace metals, particularly in FGD wastewater. So as you combust different coal sources, you actually change or have the potential to change your concentration in your FGD wastewater by orders of magnitude. So, ensuring that our treatment trains are adaptable is a key priority for the power industry. The second takeaway is really that the non-steady state operating conditions increase the risk of cascading failures and necessitate really highly coordinated water treatment and power operations. So on one hand, we really want that adaptability, but we're also recognizing that non-steady state operation is complex, it's not trivial, and there's likely to be a real role for automation in coordinating between the power generation and the water treatment aspects of the power plant. Also the air pollution control devices that are installed. And then finally, the reality at a number of these plants is that there's simply rapidly evolving economic and regulatory environments that, quite frankly, are incentivizing an adoption for low capital cost treatment trains in order to minimize the risk that you've invested in a very large piece of water treatment infrastructure that isn't going to be used for very long. And so we're seeing increasingly a preference for low CapEx, high OpEx installations over what we would see as a more energy efficient option, but often requires higher capital costs. Great. So across all of these roadmaps, we identified some key innovation needs summarized by A prime. So autonomous, precise, resilient, intensified, modular, and electrified systems. Again, I kind of highlighted the need for autonomous systems and resilient systems. There's a tremendous amount of opportunity for research in precision separations of some of these trace contaminants, things like arsenic and selenium, lead and mercury. But across power, we saw a real opportunity in each of these A prime areas. So I want to move on and just share a little bit about the work that my group has done in kind of some forward-looking analysis to assess other challenges associated with decarbonizing the electric power sector. And this is not NAWI work, but I think it really complements and builds on some of the water challenges of the present that NAWI has dug into, and helps us also think about what are the challenges that maybe are a little bit less germane to the power industry today, but may become really important in the near future. So one of those is some recent research that myself and Tim Bartholomew, who's actually now an NETL employee, has done on understanding how we might manage the produced brines from large-scale CCUS. And this is an image from NETL. I apologize, I did not properly cite it, but essentially, the message here is that as you inject CO2 into the subsurface, you're building up pressure in these saline formations. And so one of the opportunities to enhance the storage capacity and reduce the buildup of excess pressure is to sort of withdraw some of these brines and potentially send them for beneficial reuse or disposal. So we did a thorough analysis of likely CO2 saline reservoirs across the US. And one of the things that we found is that while there's tremendous variability in the salinity, both within and between reservoirs across the US, the median total dissolved solid concentration is 100 grams per liter. So that's about 3 times the salinity of seawater. They are very salty. And with that comes a number of technology challenges, because this is the sort of range of waters that we have the sort of least cost-effective and energy-efficient strategies for desalinating, both because there's a larger thermodynamic penalty of performing that separation, but also because those processes operate at much lower efficiency and higher cost. So there's open question about how much treatment do you want to do, what technology do you want to deploy. Certainly there are beneficial reuse opportunities for some of that water, but the costs of recovering it are likely to be very high. But there's also limited disposal capacity. And so this is a real balance that we are going to need to strike going forward. I think the big takeaway from our analysis, and I haven't gone into it much detail here, but this treatment, if we do choose to treat a large fraction of it, would impose sort of an extensive energy penalty on the plants. So when we think about CO2 capture and compression as having energy penalties or imposing energy penalties on the plants, depending on how much reuse you choose to deploy, you're looking also at increasing that energy penalty by another 0.1 to 2%. The other takeaway from this, and I think this is actually the most interesting one, is that because brine management energy consumption is likely to be an order of magnitude higher than CO2 transport and storage, it may make more sense to transport CO2 longer distances in order to tap lower salinity reservoirs. It at least makes carbon sense. It may not make economic sense, but there's some real questions on how you're going to design these CO2 distribution networks and where you're going to choose to inject that CO2 into the subsurface. Clearly, there are many other objectives that you're also going to optimize on, but this is, I think, an important one to include. I would just echo what I said earlier, which is that the energy demand of this brine management can be reduced by selecting reservoirs with lower salinity, developing some energy efficient separation technologies for high salinity brine, which is a key mission of NAWI's intensified brine management efforts in our first year funding opportunity announcement, as well as identifying alternative large scale disposal options. I want to sort of wrap up really by sharing some other work that we've done in thinking about how major shifts in the energy sector are really going to radically change water treatment needs. And the A prime concepts that I laid out, I think are going to enable very similar transitions for water sector as the transitions we've seen across the energy sector over the past 30 years, particularly mirroring some of the on-site and on-demand attributes of next generation power production and the flexibility that affords to power networks. I think in adopting A prime, we're going to start to see much more diversification of sources, decentralization of treatment and source supply, decarbonization of these sources, decoupling of supply and demand, and a big focus on energy or water efficiency or demand softening. But I think we can also start to think about the benefits of synergistic operation between the power sector and the water sector. So I think these 5D concepts that I've laid out here increase operational flexibility independently, but the greatest potential flexibility, efficiency, and resiliency benefits are really going to come through coordination between power systems and water systems. Realizing this coordination is obviously going to require some pretty high spatial temporal model resolution and computational frameworks. This is not a trivial proposition, but I think it's one in which there's some really rich opportunities for research and partnerships across sectors and between the sort of academic research community and the industrial community. So I want to highlight just very quickly some opportunities where I definitely see sort of the potential for coordination. And one is in using water systems one example is in using water systems to provide demand response services to the grid. So there's an opportunity to potentially provide pretty significant amounts of demand response because water supply systems consume a good deal of electricity, especially if you include both water treatment, water distribution, water transmission, and wastewater treatment. The second attribute that makes this kind of attractive is that there's a great deal of time flexibility in the electricity consumption of the water sector. There's built-in water storage. There's a potential for electrified treatment, and also the on-site storage and generation combination enables quite flexible electricity load, particularly at wastewater treatment facilities. And then finally, I just say that a lot of the energy consumption is coming from pumps, which can stop very, very quickly and have the opportunity to provide different types of energy services to the grid. So we've recently developed a model that has looked at the potential for demand response throughout the water supply chain. We see a lot of demand response in transmission today. We see much less of it in treatment and distribution. And so we're really interested in applying this concept of marginal energy intensity for specific water users to help us reduce electricity bills for water utilities, which provides direct benefits and incentives, but also to realizing carbon reduction goals without costly infrastructure upgrades and determining where and when to shed excess electrons from the power sector and use those in the water sector. So I just want to wrap up by saying that I have a couple of predictions for water energy nexus research over the next sort of 9 years. I definitely expect remaining coal plants to face increasingly stringent water quality discharge standards, and those plants should probably, are thinking about that right now. They've been thinking about that for the past decade, but it's certainly going to be a major driver. As I mentioned, and Tim also mentioned, these plants are going to more frequently tap non-traditional water sources. We need to support them with a set of water treatment technologies that make that cost-effective and feasible. I also think that water will become a very important selection criteria for decarbonization pathways. So we've seen that the transition to decarbonized sources will radically change not just the amount of water that's consumed, but also the spatial temporal distribution of that water consumption. We've talked a lot about how geologically sequestering carbon may require a huge buildup in hypersaline brine treatment capacity, and certainly begs for new technologies that are more efficient and more cost effective. And then, as Tim mentioned, really understanding the full life cycle of water consumption. So the water that goes into producing that biomass is similarly important to assessing the feasibility of some of these decarbonization approaches. And then, finally, I'll just conclude by saying I think that the water utilities have the potential to become a viable DR provider. They almost very, very few of them are engaged in that right now, but I think both the scale and the potential for real coordination is a viable place to provide energy services and spend excess electrons. And with that, I'm going to pass this back to Briggs and Alex to take questions.
Great. Thank you so much, Briggs, Tim, Megan. This was a fantastic webinar on really such an important topic. So we very much appreciate you guys taking the time to discuss this. Briggs, I'm sorry I interrupted you, so I will mute myself and let you finish.
No problem. And yeah, just have a few summary remarks here just to bring us to a close. What we heard from Tim and Megan in their great talks is that there's a large number of opportunities. Understanding the energy water nexus through very integrated analysis of these systems is incredibly important. Lots of opportunities for innovation for the existing fleet, a significant asset base, a highly capitalized asset base that needs to be considered. Lots of innovation for dry cooling, non-traditional water treatment, including treatment of those really high TDS brines associated with CCS. As Megan commented, significant challenges and opportunities and needs with respect to effluents and opportunities there to reuse those waters as an alternative to non-traditional water treatment. Enabling the hydrogen economy, whether it's gray, blue, or green hydrogen, there are significant water implications and those need to be taken into account. And then finally, innovation, and I wanted to point out business models. As Megan was pointing out, there's a lot of coupling that's going on in terms of bringing together different users. And so the business models have to make sense in order to drive deployment. In terms of our fossil energy program, I will just comment that we are sort of covering all the bases in terms of existing and next generation thermoelectric fossil plants with a heavy emphasis on a lot of the opportunities that you've just heard about. And I wanted to highlight an FOA that we have currently on the streets. It closes at the end of January, where we're providing funding that addresses treatment of water, whether it's from non-traditional water, water within the plant, or water associated with CCS. And it has to be tied to a power plant. So trying to improve that water treatment process. If you're interested, please check it out or contact me. And with that, we do come to the Q&A session, and we really do welcome your input and feedback. So please let us know your thoughts.
All right, thank you, Briggs. And again, I apologize for jumping the gun there for a second. We have had numerous questions come in, and we still have some time to answer them. So we will do our best to answer as many as possible and the allotted time. So the first question is for Tim. What are the prospects for making use of wastewater streams, especially produced water from oil and gas operations?
Thank you for that great question. As Megan touched on, a lot of those are high intensity, very brine or salty waters. And so a lot of the work that's being done in the research programs around brine management is what will maybe enable some of the use of the oil and gas waters. However, I will remark that we have to have alignment between the right water volumes being produced and the needs. And most oil and gas operations, particularly gas extraction, have high water volumes in the very beginning for use and treatment. But after that first initial time period of a few weeks to a month, their water production significantly decreases at a well-to-well level. So we do need to align the resources correctly from the water production from a cost view to determine if it's feasible to transport that. But the work in the research programs, both within the Department of Energy and those that Megan alluded to with the NAWI program, are critical to enabling those high brine water to be able to be reused as an alternative water supply. I will allow, Megan, if you had something you wanted to offer on that context as well, I'll give you the opportunity.
No, I think you did a great job. Certainly matching supply and demand is a big part of a lot of these challenges. And what we've seen is that the transport costs of water are just, crippling for a lot of these non-traditional water uses. And so on-site reuse tends to be a really powerful alternative to long distance transport.
Great, thank you both. Tim, another question for you. Given that available biomass, available water resources, suitable coal-fired power plants, and favorable CCUS opportunities are geographically distributed and independent of each other, has a study been done looking for low-hanging fruit of coincident occurrence of these resources?
So thank you for that question. In the context of one unified national study that aligns carbon capture, biomass co-firing, and other opportunities together, there's still there's not one model that's going to give you that golden answer. There are a lot of studies out there looking at regional opportunities, whether they're biomass co-firing in relation to where the biomass supply is. Within the Department of Energy, the Biomass Energy Technology Office has done a lot of work on biomass resource availability, which we leverage within the Office of Fossil Energy to kind of understand the synergistic opportunities. And so these are things that continue to be explored as we move forward. But I can't point you to one single study with a golden answer at this time. But thank you for that question.
And thank you for the answer, Tim. Megan, we're gonna move over to you. A couple questions for you now. Is there consensus on how much produced brine is expected per unit of CO2 storage?
Yeah, that's a great question. It's actually something that I think is poorly defined at a reservoir level. We surveyed all of the literature that we could find from both the peer review literature, but also actual sort of test sites, some of NETL's best sites. And the expected brine extraction ratio, so that's the relationship between the volume of brine extracted and the volume of CO2 injected, is about 0.2 all the way up to a 1-to-1 relationship. So that's 0.2 cubic meters of brine per cubic meter of compressed CO2, all the way up to a 1-to-1 ratio. So when we did this analysis, we performed a Monte Carlo analysis that spanned that distribution. There's a number of other variables that were also included in that Monte Carlo analysis, things like disposal reservoir pressure, CO2 density, et cetera. But I think that's a real opportunity for further research, especially as we drill down and, no pun intended, but really start to understand the different qualities of these CCUS formations.
Great, thank you. And following up on that, regarding considerations for CO2 storage in a saline formation, are there any concerns related to changing the formation similar to concerns with hydraulic fracturing?
Yeah, so the overpressure in these formations is certainly a risk, and that's one of the reasons that you would withdraw these saline brines. I am not a subsurface geologist, and I'm going to stop commenting because I am far outside of my domain expertise, but in speaking with experts in this field, there's sort of a strong analogy to any sort of deep well injection phenomena where a lot of it has to do with the rate in which you are trying to inject that CO2. So when you're starting to think about actually building out the infrastructure to do the storage, you're not going to want hundreds of thousands of wells. You're going to want wells that are able to sort of move CO2 into the subsurface quickly and at fairly high rates. And that's especially where you're likely to run into challenges, from my understanding.
Got it, thank you. A couple questions that, again, might be slightly out of our wheelhouse, but I'm gonna ask them anyway. You've talked about brines as a source of usable water. Are there situations where brines could be used as a source of usable minerals?
Yeah, so we have a topic area within NAWI that's focused on precision separations. And as part of that, we're really interested in the transformation and valorization of some of these concentrates. And I think that, again, there are always challenges in terms of what's the actual concentration, what are the separations technologies, what's the market, what's the purity requirement to sort of sell into that market, and how does the transportation cost and sort of the logistical costs impede the economic viability of these propositions. But we're certainly interested in exploring this from a scientific perspective and trying to harvest valuable rare earths where it makes economic sense.
And Megan, I'll just jump on and say that the funding opportunity I mentioned there towards the end also identified that particularly for non-traditional waters, whether it's the CCS brines or otherwise, there may be in fact additional minerals or other valuable materials that can be separated. So clearly that's definitely of interest.
And then we have another question. Is biomass still seen as a negative carbon option? There's been some revisiting of this issue appropriately. Considerations of time frame and baseline comparisons is necessary. Dedicated crops that were not part of the natural environment in the first place.
Thanks, Alex. That's a good question. Currently still from the EPA regulated and determined that biomass, the carbon removed from the atmosphere that is then retained within the biomass that is harvested, is considered neutral from that perspective. You still need to account for the energy intensities associated with any of the management of the land, preparation of the land, management of the land, as well as the harvesting and processing of that biomass for use. It is and will remain an open area in the science around whether or not it's truly neutral or not. And we look forward to continuing to participate in that body of literature and that science around that understanding from a life cycle perspective. And so thank you for that question.
And again, thank you for your answer and all of your answers. We are a couple minutes past our closing time, so I would like to be respectful of everyone's time. We will follow up with all of our attendees and registrants once we've posted a copy of the presentation as well as the recording of today's webinar. We will include a link to our event page in case you don't have it. If you have any questions that unfortunately weren't answered during this webinar, please feel free to email those to me and I can send them to Briggs, Megan, or Tim. Thank you everyone for joining us today. Our next webinar will be on January 25th, looking at the finalization of the 45Q tax credit as well as other provisions relating to CCUS within the omnibus. Briggs, do you have anything final you'd like to say? And if not, I will go ahead and wish everyone a good day.
I'd just like to thank USEA for hosting us here. Megan and Tim, great job with the presentation. I know a lot of work went into that. And to thank all of our stakeholders, thank you for attending this webinar and generally supporting the Department of Energy and working with us as great partners. We really appreciate it.
Great. Thank you all and have a good, safe, and healthy rest of your day and rest of your week.
Thank you.
Bye.
Bye.